Well, hello everybody, Dave here, and this is lesson 1 in a series of lessons on the idea of sets and set notation. If you've never seen a diagram like the one on this front page, by the end of this lesson, you'll know what it is. So before we get going on the mathematics, we have to understand the language that we use to describe the idea of set notation. So here are 5 of the most common words that we're going to use today. However, there will be some other words that we bring up over the course of the lesson. Set, by definition, is just a collection of distinguishable objects. You'll see that I've given you a definition of W, which in this case is going to represent whole numbers, and then you'll see that I use squiggly brackets. It's important that you use these squiggly brackets to contain the set as opposed to the round brackets, as this is the classic notation. So in this case, I'm listing off the elements, 0, 1, 2, 3, and so on and so forth. An element, by definition, then, is just an object within the set. If we wanted to talk about a scenario like rolling a die and writing out all the possible outcomes of that roll, what we end up with is the set S, which in our case is 1, 2, 3, 4, 5, 6, and that for this scenario of rolling a die would be the universal set. So the universal set, by definition, is all the elements contained within a given scenario. If we wanted to take, say, the odd numbers of the possible rolls, that would be actually selecting a subset of that universal set. So in this case, if we let O be the set of odd digits, then 1, 3, and 5 by definition would be a subset of S. Every single element in a set has to be present in the universal set for it to be deemed a subset. So for example, if I had the numbers 1, 3, 5, 7, well, 7 is not actually in the universal set, therefore that set that I just listed wouldn't be a subset of the universal set. At the same time, if we take a look at the complement of our set O, what we would be finding is all the elements that are not in the set O. So in the case of the universal set of 1, 2, 3, 4, 5, 6, we've already identified that 1, 3, and 5 are the set of odd digits, so not O would be equivalent to the even digits, which in our case are 2, 4, and 6. And so you'll notice that these two sets, O and O prime, don't share any elements, which makes them complementary to each other. So you can see just by the list of these 5 words that not only are the definitions important, but also the notations associated. Please remember that this apostrophe on the letter represents the complement and not just simply an apostrophe. So let's get into an example that uses sets. Let's take the country of Canada, and we would like to categorize Canada's regions. So the first thing we want to do is list off all the elements which would represent the universal set of the Canadian provinces and territories, and we're going to label that as C. And so I've chosen some 2-letter abbreviations, and again, you could choose whatever you want. You could also just write out the words. But you'll notice that again, we have all of the territories and the provinces listed in this set, enclosed by squiggly brackets, commas in between each element. Remember, these are distinguishable elements, but every single province and territory of Canada should be represented by this set. Now, let's imagine that we're going to create a subset. We're going to deal with the western provinces and territories, which in this case would be from the Yukon to Nunavut in the territories and from BC to Manitoba in the provinces. Well, if we had to draw a Venn diagram of this situation, the first and most important element is this rectangle. This rectangle represents the universal set. And so any Venn diagram that you draw has to start with this. What you draw next are all the sets that you have defined within this universal set. Remember, by definition, if we have a subset of the universal set, then all elements should be contained within the universal set. So, if we take a look at this Venn diagram, what we see is the set W represented by a circle, and it is completely enclosed by this rectangle C, which is representing the universal set, which in this particular question's case is all the provinces and territories of Canada. And so you can see clearly that if we have W representing the western provinces and territories, all the area outside of that circle, but within the universal set, represents not W, which in this case would be the eastern provinces and territories. If we continue along this question and we actually write W primed in set notation, remember that this is supposed to represent not Western provinces and territories, which only leaves the Eastern provinces and territories. Well, there are no territories to the east, but all the provinces that are listed there are certainly considered Eastern Canada. And so again, you'll notice that none of those elements in W prime exist in the set W. But if you take W and add it to W prime, you'll see that we again have all of the Canadian provinces and territories, or the universal set. This is an important definition to move forward. If we have to explain what W prime represents in the Venn diagram, well, again, in the Venn diagram, it's going to be the area outside of the circle, but inside the rectangle. That's what makes the rectangle so important, is the fact that it represents the actual universal set. So that area is representative of, in this case, the complement of W. For part D now, we're going to say that Jasmine wrote the Eastern provinces the way that she wrote them there. And the question is E equal to W prime? Well, in this case, the only way that two sets can be equal to each other is if every single element of one is in the other, but no more or no less. So in this case, you can see that all 6 elements in W primed are in fact in this set E that she wrote, which means that indeed these are equal sets to each other. If there was one more element in either of these or one less element in either of these, then even if all those elements in one are in the other, they wouldn't be equivalent sets, they would be a subset of one another. If we look at E now, and we're going to make T be the set of territories in Canada, and ask if T is a subset of C, which was the universal set of Canada. Well, of course, we know now that from our universal set, that includes all the provinces and territories, which means that every single element in T is in fact in C, making it a subset. If we talk about W, is T a subset of W? Again, we determine that all the territories are actually in the western part of the country, which means that every single element in T is also in the subset W, which makes it a subset of W itself. So there's an important notation that's written in the bottom right corner of this screen, where you see T and then a sideways U and then the letter C. What that represents is that T is a subset of the set C, which is what we determined previously. So if we have to explain if we can represent the set of Canadian provinces south of Mexico by an empty set, the term empty set is an important new vocabulary word that we have to know. An empty set by definition is a set that has no elements in them. And for those of us that know the country of Canada, we know that there are no Canadian provinces south of Mexico, which means there can be no elements within that set, therefore making it an empty set. And if we consider the sets C, W, W prime, and T, and we want to list a pair of disjoint sets, again, the term disjoint means that there is no element that is shared between the two. And if we take a look at these sets, we would be able to say that W and C are not disjoint because every element of W is in C, but W and W primed, by the definition of a complement, have no elements that are shared, therefore these would be disjoint. Another example of a disjoint pair would be W primed, which would be the eastern provinces, and T, because again, there are no elements in T that exist in W prime, therefore they are disjoint. On a Venn diagram, disjoint sets are actually separate circles. If there are elements that are shared between the sets, what you will see is an overlap like we did with the picture on the very first page. Now that we've determined what sets are and how to use Venn diagrams to explain sets, let's do something a little different and let's actually create set equations based upon a given scenario. So in this case, we want to make sets that represent all the multiples of 5 and 10 for all the numbers from 1 to 500. The first thing we need to recognize is that the universal set in this case is going to be all the numbers from 1 to 500. And so our first set there on the left is, in fact, all of those integers. But there's another way that we can represent these if we want to use more advanced set notation. And so the equation on the right says the following, that S, which we've defined to be all the numbers from 1 to 500, is equal to the set, the squiggly bracket represents the set of all values of X, such that, the vertical line says such that, x is between 1 and 500, where x is the set of all natural numbers. So that last expression at the end of the set notation, x, and then it's a funny looking e thing, n, actually states that x is the set of natural numbers. If we stated that they were all integers, integers would include the negative values, then we would say x is the set of capital I for integers. If we were going to do just any numbers, all real numbers, which means decimals are included, then it would be x is the set of capital R for all real values. So we have to watch out for this notation. The one that I didn't mention is whole numbers, which includes 0. So natural numbers typically does not include 0, and whole numbers does. Whole numbers is represented by a capital W. So that equation on the right is quite tricky, but again, what it says is put in a number for x. If it's between 1 and 500, including those values, and it is within the set of all natural numbers, then that is one of our elements of the set. And so the two equations are actually equivalent to each other. Well, let's go to the multiples of 5 now. We know that multiples of 5 are just counting up by 5 until we get to 500. So on the left-hand side, we've defined f to be this set, and in this case, 5, 10, 15, and so on, all the way up to 500, are your multiples of 5. However, if we want to define this using a set equation with advanced set notation, then we're going to let f be our set, which represents multiples of 5, but we're going to let it be the set of all values of f, lowercase f, such that, the vertical line, f is equal to 5x. Now, this is a little tricky, because what we've done now is we've actually defined an equation with a range of possible values, which in this case is between 1 and 100. Now, why is it 1 and 100 and not 1 and 500? Because we're dealing with the multiples of 5. We know that the highest value we can get is 500, where we plug in 100 for x in our equation, then the value of f will be 500. So this is an important element. This is what makes these so tricky, is to understand that the first statement is that here's this new variable f. Vertical line for such that, and now the next statement is here's an equation by which we are going to calculate f. And in this case, we're going to take all of our possible values of x, which we've defined to be between 1 and 100, where x comes from the set of natural numbers, and then we're going to take that value and multiply it by 5. And so again, both of these sets are equivalent to each other in what they represent, and depending upon who your teacher is, they will be okay with either, but certainly the one on the right is more advanced. Obviously, if we did that with multiples of 5, we could also do that with multiples of 10. So again, on the left-hand side, we've listed off the multiples of 10. And on the right-hand side, we've created this new set equation that involves the lowercase t value, such that t is equal to 10 times the value of x. And you can notice now that the domain, or the range of values that x can be, is now between 1 and 50. And why is that? Because if we look at the lowest number, 1 times 10 is 10, which is the first item in our set, and 50 times 10 is 500, which is the last item in our set. And as long as we stay within the set of natural numbers for our value of x, what we will end up with is the complete set of the multiples of 10 between 1 and 500. So, really tricky to get used to this kind of notation. Again, I would recommend playing around with textbook problems and problems that you find online and things like that to get used to this notation. But the key behind this now is we can begin to define what our subsets are. And so we know that the multiples of 10 and multiples of 5 both need to be subsets of the universal set, which is the numbers from 1 to 500. So those first two statements there, t is a subset of s and f is a subset of s, are absolutely true by definition. But what additional subset you may not have noticed is that the multiples of 10 are actually a subset of the multiples of 5, because within the multiples of 5, every single multiple of 10 exists. Not the other way around, though. Obviously, a multiple of 10 is not 15. And so it's important to recognize that even within our subsets of the universal, subsets can be subsets of each other as well. So this by far is a more challenging problem than the previous ones, but the methodology that we used in the previous problem is absolutely the same. So just get used to this notation and the language that we use. The vertical line for such that, squiggly brackets for defining the set, the statement at the end, which is stating in what number range are we talking about. Are we talking about natural numbers, whole numbers, real numbers, or integers? So now we can represent these sets in a Venn diagram. And remember that the most important element to start with is this rectangle that represents the universal set. Now we can put in our sets which represent the multiples of 5 and the multiples of 10. And you'll notice that the bigger circle, which represents the multiples of 5, encloses completely the set that represents the multiples of 10. That's because we determined that the set T is a complete subset of the set F, which means that that circle should be completely enclosed with that circle. If it was sticking out a bit and it wasn't completely inside, that would mean that there were elements in the set that are not represented by the set F. So you will see those in future questions when we talk about Venn diagrams, where there will be an overlap where some of the elements are shared, but not all of the elements. In this case, that is absolutely true. If we take a look also at what the area around the circles represents, well, if we look at the big circle first, the set F, then the area outside would represent the set not F, or F prime. And again, from that we can begin to play around with the elements, we can begin to play around with the numbers associated with these sets. So a Venn diagram is really important to get right in that it can give you a lot of information quickly, and your ability to interpret it will be absolutely essential. So let's look at our last example for this lesson. And we're going to deal with trying to understand what the pattern represents, and then once we have that pattern, how do we actually generate the sets associated with that. So in this case, we're going to define a triangular number as something that creates these triangular arrays like you see. And what they've done is they've given you the first 4 elements of this pattern. And the question that they ask first is determine a pattern you can use to determine any triangular number. The first thing we should notice, hopefully, is that depending upon what triangular number we're dealing with, if we take the sum of the values, what we get is the triangular numbers. So in the first one, 1 is 1, but in the second one, we have 1 up top plus 2 on the bottom, and we get 3. For the third triangular one, look, it's 1 plus 2 plus 3. The fourth one is 1 plus 2 plus 3 plus 4. So you can see the pattern that's starting to form here. The next triangular number would be 1 plus 2 plus 3 plus 4 plus 5. And so in fancy language, we're saying that the nth triangular number is the sum of the first n natural numbers. So now that we know how to identify a triangular number, let's go ahead and start to play around with the math. In this case, we want to determine how many natural numbers from 1 to 100 are even and triangular, odd and triangular, or not triangular. So to do that, we actually have to start off by finding what the universal set is. And we know that this is all the natural numbers from 1 to 100. So I've let u represent that, but notice now that after I write out that set, I write this funny little statement at the end that says n brackets u is equal to 100. Well, what that represents is the number of elements in set u is equal to 100. We're not looking for the sum of the values inside. We aren't looking for a specific value inside. We are just counting the number of elements inside the set u to get this value of 100. So if you look at the next set now, which is the triangular numbers from 1 to 100, we know the pattern, so we can actually just generate what these values are. And if we count up all those elements in set T, what we get as a total number of elements that are triangular numbers from 1 to 100, we get an answer of 13. So this notation is critical because what will happen are some questions will ask you to generate a set, and other questions will ask you just to count the number of elements in that set. So if you look at I now, we want to find the values that are even and triangular. Well, just based upon our set of triangular numbers, we can count the even numbers, and we've generated the set E to be these even triangular numbers, and we can see that there are 6 elements, which means that the number of even triangular numbers is equal to 6. So now for the second one, we're going to find the number of odd triangular numbers that we see between 1 and 100. And for that, we can do one of two things. We can either go back to this set of T, and we can just list off all of the elements that are odd and count them up and get our answer. We can also recognize that if we have the number of even triangular numbers, and we have the number of total triangular numbers between 1 and 100, then if we take the difference of those two numbers, this number 7 should represent the number of odd triangular numbers. And again, to convince yourself, go ahead and look at the set T and see for yourself that indeed there are 7 odd triangular numbers. Now, by definition, we've found the complement. We had the set t and we subtracted the number of even to give us the number of not even, which by definition has to be odd. Watch out for these questions because once in a while, if they're dealing with whole numbers where 0 is included, 0 doesn't count as either of those, and that would be an element that we wouldn't include. So for the last one, the number of numbers between 1 and 100 that are not triangular, if we know that there are 13 triangular numbers and we know that there are 100 natural numbers from 1 to 100, then what we can do simply is take this universal set value of 100, subtract the number of triangular, which is 13, which should give us the number of not triangular, which in this case is 87. So once we understand how sets work and what these values tell us and don't tell us, we can begin to generate values much faster just based on the fact that we understand how all these numbers play together. So the last question now is just how many numbers in general are triangular? And for this, what people tend to do mistakenly is they just go back to the original sets and they start counting and say, hey, well, there are 13. But that's not what it's asking. It's actually asking for how many numbers, period, are triangular. And in this case, we go back to the way that we found triangular numbers. We had a range of natural numbers, and we counted up how many of those were triangular based upon our pattern. Well, if we know that there are an infinite number of natural numbers, there has to be an infinite number of triangular numbers by definition. That no matter how high we count, there's always going to be one more somewhere. So everybody, that's it for this lesson. Get to those practice problems and we'll talk to you again.